To build an autonomous drone to explore unknown tunnel environments, task includes navigation, mapping, and data collection without GPS. Coming to the parts of this, the first thing is propeller, where the propeller is which enables the drone flights. Coming to the antenna, for the wireless communication we'll be using, there are three LEDs which gives an eye visibility of dark tunnels. Coming to the intel real LIDR cameras, which captures the depth data of 3D mapping and obstacle stabilizers, where stabilizers keeps the drone balance of narrow environments, and the battery indicators and the power buttons, which shows the battery level and the low power control, which is downward sensors which detects the surface of ground proximity. And coming to the onboard NVIDIA with powerful onboard compute processing of real-time data, which manage the flight stability and stability movements, and micro SD which saves the sensors data and image logos here, where battery cover we have been used battery covers, and even RGD camera. RGD camera is to capture the color depth data of IMU, which detects the motion and the orientation of the title. Coming to the system architecture, where there are cameras of module 1, module 2, and module 3, which ranges here. In this, where the sensors of camera modules like IMU, depth sensors collection and data environments takes place, and the visual front end features detection tracking, which extras the features of mapping and tracking. Coming to the backend optimization, backend optimization takes the new factors like sliding window optimization cameras, which optimize the recent data to refine localization, and color and depth cameras. We have been used IMU front end pre-integration. We have used camera eye, IMU, and image eye, which illustrates the step by step how the drone process will be taken, how the tracking has been taken from the step by step. The sliding window to optimization in the state estimation, where the path is multiple camera of visual initial systems created by fusing the visual observations from the cameras, where it has shown here the cameras and the motion data from IMUs over time. Coming to the camera and IMU, where camera I, IMU, and camera J, where three steps have been taken place, where the step-by-step process has been happened, where each camera I and J are the IMU capture data to the specified the timestamps, where the time is synchronized to ensure their measurements. To ensure the measurements can be accurate associatedly, where the camera captures the image at the time, where cameras capture the image of the time, and the visual features like corners and the key points, like this. The features are tracked across the frames to estimate the motion between to detect the each, and the features is tracked by the frames to estimate the motion between cameras and the poses, and the each frame gives an relative pose of this, the position how the oriented as take place, where IMU of the pre-integration, the motion path. IMU is considered the pre-integration, where the motion has takes place like this. It provides an gyroscopes to data the eye frequency to measures an eye integrated over the time estimation of velocity and the orientation changes, and it also takes a long term and it combined with the visual data, and the visual initial fusion takes the path estimation of this. The path estimation takes place by the system algorithms like sliding windows and optimizing or the graph based methods like fuse cameras and IMUs, and the pre-integration for the IMU helps for constrain the motion between the visual frames, and the fusion poses and corrects the errors with the tracking of IMU drift, and the path formation is to fuse the path each time step by step tragedy, and this tragedy to estimate the path of system this piece. It extracts the tracking of visual features over time for the multiple cameras. And coming to the structure of this, it shows the colored Color cameras and IMU depth cameras were used to RGB initial and map fusion to combine the depth and visual initial data, and it identifies the tunnel paths towards the precipitation. And the planning model, coming to this, to how the plan entry takes place in the tunnel of replanning to adjust the path and dynamically inside the tunnel. The post tunnel planning determines the exit route, the controllers to send the commands to motors, and to control send command to the motor execution, how the controller has been take placed. Where the start and the takeoff and the pre-tunnel, the marker detection and the tunnel entrance localization, how the pre-tunnel planning make entry and compute the initial path entry tunnel, and in the where it is an entry tunnel to the pre-planning routing exploration using RGBD IMU and the fuse map data to avoid the obstacles using LIDR sensors to exit the tunnels where it is an extra tunnel, where the final mapping logging the planned path of safe exits. The conclusion of this is to the autonomous drone systems to design for the safe and the efficient exploration of the tunnel environments where GPS is unavailable, and which combines advanced vision, RGBD, LIDR, and IMU sensors to map the surrounding and navigate the real time. The powerful onboard computers to handle the high level computations where the flight controllers ensure the stable movements. The system architectures to ensure the accurate localization, mapping, the features of tracking, data fusion, and the backend optimization. The workflow show enables the full tunnel exploration for the pre-entry planning to adaptive and tunnel navigation exit strategies. Coming to the overall, this a project demonstrates and robust and the intelligent drone solution to search and to ensure and secure the inspection of exploration to combine GPS data and environments where the human intervention doesn't take place.